Imagine for a moment absolute silence. You are floating in the deepest, darkest corner of space, far away from Earth, far away from the comfort of our sun. Ahead of you lies a region of space where the stars seem to vanish. It's not just empty. It is a void so profound that it feels like a tear in the fabric of reality itself. You are looking at the most destructive, most mysterious, and most powerful object in the known universe, a black hole. For decades, they were just mathematical ghosts, errors in equations that physicists hoped didn't actually exist. But today we know they are real. We have heard their collisions ripple through gravity, and we have even taken their picture. But looking at one is safe. Falling into one, that is a journey from which no traveler has ever returned. What would happen to your body? What would you see? Would time stop? And where, if anywhere, would you go? Today we are going to take that one-way trip. We are going to dive into the heart of darkness to answer the ultimate question. What happens if you fall into a black hole? Part 1. The Gravity Trap. Before we take the plunge, we need to understand exactly what we are dealing with. A black hole isn't actually a hole in the way we usually think of it. It's not an empty cave. It is the exact opposite. It is a massive amount of matter packed into an incredibly small space. Imagine the Earth. It's huge, right? Now, imagine crushing the entire Earth, every mountain, every ocean, every city, down to the size of a sugar cube. The gravity on the surface of that cube would be so intense that nothing could escape it. That is the essence of a black hole. It is a place where gravity has become so strong that the escape velocity, the speed you need to break free, exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing can escape. Not radio waves, not X-rays, and definitely not you. Most black holes form when a massive star dies. The star runs out of fuel and collapses under its own weight, imploding with such violence that it punches a dent in space-time that never heals. So here you are, floating in your spacesuit, drifting toward this cosmic monster. Part 2. The Approach and the Photon Sphere. As you drift closer, the first thing you notice is that the black hole isn't actually black. Surrounding the dark center is a swirling, glowing ring of fire. This is the accretion disk. It's made of dust, gas, and shattered planets that have been caught in the black hole's gravity. This material is spinning at a significant fraction of the speed of light. Friction heats it up to millions of degrees, causing it to shine brighter than 1,000 suns. If you were unprotected, the X-rays and radiation from this disk would fry you instantly. But for the sake of this journey, let's assume your spacesuit is indestructible. You pass through the chaotic storm of the accretion disk. Now, things get weird. Gravity is bending light around the black hole like a lens. The stars behind the hole aren't blocked. Their light is warped around it, creating a halo. The sky looks distorted, like you are looking at the universe through a funhouse mirror. Then you reach a specific point known as the photon sphere. This is a magical boundary. Here, gravity is so strong that light itself orbits the black hole. If you could pause here and look to the side, you would see the back of your own head. Photons reflecting off your back would travel all the way around the black hole and hit your eyes. You are effectively seeing a selfie taken by gravity. But you can't stay here. The pull is too strong. You are falling faster now. The dark circle in the center is growing larger, swallowing your view of the universe. You are approaching approaching the event horizon. Part 3. The point of no return. Time dilation. The event horizon is the most famous boundary in astrophysics. It is the point of no return. Once you cross this invisible line, there is no engine powerful enough to pull you back. Even if you could turn into a beam of light, you would still fall inward. But here is where reality splits in two. According to Albert Einstein's general theory of relativity, gravity affects time. The stronger the gravity, the slower time moves. This creates a terrifying paradox. Let's imagine you have a friend watching you from a safe distance in a spaceship. To you, falling into the black hole feels normal. You look at your watch, and the seconds tick by. 1, 2, 3. You cross the horizon, and nothing dramatic happens immediately. You just glide into the darkness. But to your friend watching from the spaceship, something completely different happens. As you get closer to the event horizon, they see you slow down. It looks like you are moving through molasses. The light coming from your body starts to stretch out. This is called redshift. Your image turns redder and dimmer. To your friend, you never actually cross the horizon. You just get slower and slower until you freeze in time, hovering just above the edge of the abyss, fading into infrared, then radio waves, until you vanish from sight. To the outside universe, your image is frozen there forever, a ghost on the edge of eternity. But you are already inside. Part 4. Spaghettification. Now that you are inside the event horizon, your fate depends entirely on the size of the black hole. This might sound counterintuitive, but you actually want to fall into a supermassive black hole, like the one at the center of our galaxy. If you fall into a smaller, stellar mass black hole, you are already dead. Why? Because of something Stephen Hawking and other physicists called spaghettification. It sounds funny, but it is horrifying. Let's imagine you are falling in feet first. The force of gravity from a stellar mass black hole is so immense over short distances that the pull on your feet is billions of times stronger than the pull on your head. This difference in force is called a tidal force. This tidal force stretches your body like taffy. The tidal forces become so extreme that the human body can no longer hold itself together. You are stretched into a long, thin stream of matter, pulled inexorably toward the center. You become a long, thin stream of atoms, spiraling towards the center. You are literally turned into a piece of human spaghetti. But let's assume you were smart. You chose to fall into a supermassive black hole. Supermassive black holes are billions of times heavier than our sun, but they are also much larger. This means the tidal forces at the event horizon are weaker. You could cross the point of no return without feeling a thing. You are alive. You are inside. Part 5. Inside the event horizon. Once you cross the event horizon, the universe behind you changes. Looking back, you see the stars of the galaxy condensing into a bright, shrinking circle of light. It's like looking out of a tunnel that is collapsing behind you. But inside, darkness. Absolute darkness. There is no light here because light cannot escape the center to reach your eyes. Even if you shone a flashlight ahead of you, the beam would curve down into the abyss faster than you could see it. This is where the laws of physics as we know them begin to break down. Space and time swap roles. Outside the black hole, you have freedom in space. You can move left, right, up, down, but you are forced to move forward in time. You cannot stop tomorrow from coming. Inside a black hole, space becomes like time. It flows in one direction, towards the center. No amount of thrust can stop you from moving towards the singularity, just as no amount of effort can stop you from moving towards next Tuesday. The center is inevitable. It is not a place. It is a moment in your future. Part 6. The singularity. And finally, you reach the heart of the beast, the singularity. According to general relativity, this is a point of infinite density and zero volume. It is a place where space and time cease to exist. All the mass of the black hole, stars, planets, gas, and now you, is crushed into a single point. At the singularity, the laws of physics simply stop working. Our math gives us infinity, which is just a fancy way of saying we don't know. Some theories suggest the singularity is a bridge to another universe, a wormhole. Others suggest it's a quantum foam where space and time are meaningless. But for you, this is the end. Your atoms are ripped apart. The information that made you is scrambled into the chaos of the singularity. You become part of the black hole. Your mass adds to its mass. Your energy adds to its energy. Part 7. The black hole paradox and Hawking radiation. But wait, is that really the end? In 1974, Stephen Hawking made a discovery that changed everything. He realized that black holes aren't completely black. Due to quantum effects near the event horizon, they emit a faint glow of particles. We call this Hawking radiation. Over trillions and trillions of years, a black hole slowly loses mass through this radiation. It evaporates. Eventually, even the largest supermassive black holes will shrink and disappear in a final burst of energy. But here is the catch, the information paradox. Quantum mechanics says that information can never be destroyed. If you burn a book, in theory, you could reconstruct the book from the ash and smoke if you had a powerful enough computer. The information is still there, just scrambled. But if a black hole evaporates completely, where does the information about you go? Did you disappear from the universe entirely? Physicists are still debating this today. Some believe the information is encoded on the surface of the black hole, like a hologram. Others think it leaks out in the Hawking radiation. So in a way, you might not be gone forever. You might just be transformed into scattered particles of light, drifting through the cosmos until the end of time. Conclusion: the ultimate mystery. Falling into a black hole is a terrifying thought. It is the ultimate unknown. It is a journey where space becomes time, where light freezes, and where the laws of nature crumble. It is a reminder of how strange and wonderful our universe really is. We are made of star stuff, contemplating the death of stars. While we will never send a human into a black hole, we can continue to study them from afar. We listen to their collisions with gravitational wave detectors like LIGO. We photograph their shadows with the Event Horizon Telescope. Every discovery brings us closer to understanding not just black holes, but the nature of reality itself. Thank you for watching. If you enjoyed this journey into the abyss, make sure to like and subscribe for more deep dives into the cosmos. Until next time, keep looking up.